there's going to be many applications of antiderivatives. And I just want to start talking about one, and that's finding area. So in this problem, I have a graph, and in geometry and in some of your other classes, you might have found area of like known shapes. This area isn't a known shape. It's this weird curve. And so one thing that I could do is I could break this up into known shapes. Like I could break this into like a rectangle here, and then maybe like approximate with a triangle here, and then another triangle here. And so I could break this up into a lot of different regions and find the area of each and every one of those. Those would still be approximations. I might be able to zoom in and get closer and closer and closer and closer and closer. But we need a way to do this better and more accurate. And so the way that we are going to do that is with the antiderivative. It is with integration. So I'm going to introduce you to what that notation looks like. In calculus, you might have seen this little cursive S. It doesn't really have the full S. It's kind of just this curvy S. And that is the sign for integral. Okay. When we have bounds on this, so like from here, I'm going from A to B, then we call that a definite integral. And then inside here, we call this the integrand, okay? And what this symbol means is I need to take the area. I'm going to add this all up. This is an S because it means sum. I need to add up this area where my heights are determined by f of x. And we'll talk about this dx a little bit more as we go through this, but my widths are determined by x. So think about like if you had like itty bitty little rectangles that you could make all the way across this, where your height of your rectangle is dependent on your function value, your outputs, and then the width of each one is dependent on x. And then you want to add all of those up across that interval. This is going to find you the area. Okay. And in particular, it's going to find you the area between f of x and the x-axis from x equals a to x equals b. Let's look at an example here with a line. So I want to find the total area between this function and the x-axis from 0 to 6. Well, let's go ahead and graph f of x equals x minus 2. So I go to -2. I have a slope of up 1 over 1. And I need to go out to 6. And so I'm finding the area between this function and the x-axis from 0 to 6. So notice here, no curves, it's a line. I have two triangles. So triangles, area of a triangle is 1/2 the base times the height. So this would have a base of 2 and a height of 2. But notice my height is actually like -2. And so we actually call any area that's below the x-axis, we call that negative area. So here, if I do 1/2 my base times my height, I am going to end up having negative area because I have negative height, if that makes sense. So I end up getting that this area is -2. And then over here, I have positive heights. Let's see, I have 1, 2, 3, 4 as my base, 4 as my height. So this area is going to be 1/2, 4 times positive 4 for my height, and I get 8. So what that means, it says total area. So that means my total area, I would combine all of the pieces, I would add them up, and so I would have 8 plus -2, or 8 minus 2, which is 6 units squared. Now, a concept that comes up, and there was not an example in the online textbook, so I'm just going to kind of write one down here. A concept that comes up a lot with this is velocity and distance. So velocity is change in x over time, right? And so if I need to figure out a change in x, I could multiply and I could say that distance must then be velocity times time. Well, then if I have a velocity curve, v of t, and I want to know how far something has traveled over a certain time interval, then I can take each and every velocity output and multiply by the time in which it occurred. Well, that's infinitely many of those, right? Because this time interval, like that's a continuous time interval. We'll talk about some approximation methods as we go through this, but the concept would be is that I could take each and every velocity, multiply it by its time, and then add all those up to find the distance. So if I needed to find from, we're going to say the integral from 0 to time a, and I'm going to take each velocity output and multiply that by its change in time. Now remember, we say change in time in calculus as dt. And then this says add all of those up over that time interval. And so that distance would be that area. Now let's just say that you have a velocity function that has positive and negative velocity. Because remember, positive velocity means the particle is moving to the right, and negative velocity means the particle is moving to the left. So you might have a velocity curve that looks like this. Okay, so velocity, I'm moving to the right, I'm moving to the right, I'm moving to the right. Velocity is constant, so there's like no acceleration. Then maybe I'm slowing down to 0, and then maybe I'm turning around for some reason. Okay, so that's kind of like a concept of what's going on here with positive and negative. Well, if I want to figure out like where is the particle or where is the car or anything like that, then you're going to end up using this positive and this negative, because if I think about this maybe like on a number line, the particle is moving to the right, moving to the right, moving to the right, same speed, same speed, same speed. We say here it slows down, like think about your speedometer is going to 0, so slows down. Here is when the particle changes from right to left. So I'm going constant speed, slowing down, turning around, speeding up in the left direction, and then slowing down to 0, right? So that might be where the particle is. Well, I want to make sure you understand that total distance traveled here and back is different than just like the change in position over time. So if you just need to figure out like, here's my start and here's my end, like where is the particle when I end at A, then we'll keep this as positive. And then we'll keep this as negative because we want to make sure we backtrack the particle moving to the left. But if I want to find this as total distance traveled in particle motion, then I actually don't treat this as negative because the particle is still moving. So you would need to figure out, okay, well, when is velocity 0? Like when does this turn happen? Calculate this piece by itself for that distance, and then add this piece here.